So far we've introduced the concept of energy as a natural currency, and we took a bit of a mathematical detour to introduce the dot product. Now we'll start to bring it all together with the Work-Kinetic Energy Theorem. And the Work-Kinetic Energy Theorem actually starts from Newton's second law of motion. Now I'll go ahead and do this in one dimension, and then later I will ask you to trust me that it can be generalized into 3 dimensions. So if we look just in the x direction, and we could call it y or z for all the difference in the world that would make, the Newton's second law would be saying that the net force in the x direction be equal to m times the x component of the acceleration. Now, I'm going to do a little math trick here. This comes from the chain rule in calculus. So if we take a look at the x component of the acceleration, by definition, that is the time derivative of the x coordinate of the velocity. Now, by the chain rule, what I can do is I can instead write this as dvx dx times dx dt. But dx dt is the x component of the velocity. So we can write that the x component of the acceleration is equal to the x component of the velocity times dvx dx. This is actually a super useful trick in later courses. So if you go beyond this level of treatment, you'll find that this trick will keep showing up like a bad penny. But here, for what we're doing with this treatment, we're only going to need this trick once, and we're going to need it right here. So we will now go ahead and say that f net x is equal to m times v sub x dv sub x dx. And now I can go ahead and rewrite this as f net x dx is equal to m v sub x dv sub x. Now what have we done here? What we've done here is we've got our net force, which could depend on all kinds of things. This term looks maybe a little scary, but this term over here involves nothing but v's. And so what we can do is integrate both sides of the equation. And we'll do a definite integral. So we will integrate this from x initial to x final, f net in the x direction dx, as long as we do the same thing on the other side. Now the mass is a constant, so I can pull it out of the integral. So as long as I integrate this from vx initial to vx final, I have I'm integrating v sub x dx. All right. So remember, so we've seen this one before. Sorry, not dx, dv sub x. So what this is a function of, if I just go ahead and make a plot off to the side, is the function is just vx given vx. So it's the 45-degree line. And our limits of integration are vx initial to vx final. And as we've seen before, we can write these definite integrals as the area under the curve. So this area right here is equal to this integral right here. And then I'll have to times it by m at the end. But this is a trapezoid. And so it will be the base times the average height. So this is 1/2. So the average height will be Vx initial, because this is Vx initial as well. This is Vx final here, so Vx initial plus Vx final. Oops, let me move all this over. There we go. Times this width here, which is going to be Vx final minus Vx initial. So this whole area under the curve will equal 1/2 Vx final squared minus Vx initial squared, once you do the whole foiling and canceling. All right, so then this gives me whatever this is on this side. So I'm just going to say integral from x initial to x final of the x component of the net force dx. And this will equal m times this whole integral we said was 1/2 x final squared minus Vx final squared minus Vx initial squared. So this is 1/2 m Vx final squared minus Vx initial squared. And I can rearrange that just a tiny bit more. I'm going to write this as 1/2 m Vx final squared minus 1/2 m V initial, Vx initial squared. Now, since all the motion's happening in one dimension, I could have just dropped all the x subscripts and called it V and been done with it. And then I would realize that, hey, this is the kinetic energy that we saw a couple of videos ago. So by definition, this is the final kinetic energy minus the initial kinetic energy. And while we're at it, what we're going to do is we're going to take this Gacky integral here, and we are going to define this as the work done by our force. And the symbol for work is a capital W. So what we end up with here is that the net work, this is actually the net work since it's the work done by all the forces, and I will more rigorously define work in a second. What we get is that the net work is equal to the change in kinetic energy. So often we just write it as W net equals delta K. So, all right, so let's try to make a little more sense of this. Now, to do this, I'm going to have to ask you to just trust me a bit and say that this does extend into 3 dimensions. I won't give the reasoning other than I won't derive it other than say the reasoning is similar but a little more tedious. But you end up with saying that the work is equal to is defined to be the integral from the initial position to the final position of F net dot, that's our dot product that we saw in the previous video, ds, where this is a differential of displacement. Sorry, a differential along our path. Now, this expression is more complicated than we need. I just want to say that this is the general case, and this will come back when you do electricity and magnetism later. For now, if you don't understand what all the symbols mean, like this, that's fine. What we'll do is we'll go ahead and look at the cases that we're going to need. So with that, let's go ahead and more properly say what work is. So now that we've run across it, we can say that work, first off, is something that is done by forces on objects and is the result of a force being applied through a distance. THRU, yeah, through a distance. So we'll start with the case of a constant force. If the force is a constant, so let's just say for now we have a force, it'll look something like this, let's say, and we'll have a displacement, looks something like that. Now I draw my displacement arrows funny compared to my force arrows, and this is just so I can tell quickly this is a force, that's a displacement. What this Feldergarb here that we had for the case of a constant force looks like is if we go and put the R2 vectors tail to tail like so, force delta R, we'll say the angle between them is phi. We can say that the work done is equal to the force dotted with the displacement. So again, we can write this as, for instance, F parallel, this piece right here is the force that's parallel to the displacement times the displacement, or we can write it as F times the displacement times the cosine of the angle between them. Now, our units here, if we take a look at this, we have force and we have displacement. So this is newtons, this is meters. However, we always write this with a capital J and call it a joule. And this is equal to 1 Newton times 1 meter. Don't write Newton meter. That's because we will see Newton meters later as a unit for torque. Torque, it turns out, will be describing the effect of a force being applied at a distance trying to rotate an object, whereas work is describing the effect of a force being applied through an object to change its speed. Because after all, from the Work-Kinetic Energy Theorem, what we get is if there is net work done, the kinetic energy changes, but the kinetic energy only changes if the speed changes. So anyway, the difference between at and through is crucial, but doesn't show up in the physical dimensions. Both of them are newtons times meters. So in order to keep them straight, we always write energy, works and energies as joules, and we will write torques when we get to them as Newton meters. So don't write Newton meter if you mean energy. Write a capital J for joule instead. So we can interpret the sign. So we can interpret the sign of work be if the work is positive, that means that our object will be speeding up. And this is because our part of the part of the force that's parallel to the displacement is responsible for changing the speed. This bit here, just for completeness sake, is the bit that's perpendicular. We don't care about this at the moment. But remember, the bits of force that are perpendicular to displacement are responsible for changing direction. The bits that are parallel are responsible for changing speed. So for the dot product to be positive, this angle phi here has to be between 0 and pi over 2, or 0 and 90 degrees, to give us a positive cosine. So in that case, the force is being applied roughly in the same direction as the displacement, which means you'd be speeding up. Similarly, if the sign is negative, that means the object is slowing down. So in that case there, you would be looking, that would happen if we had an angle that was bigger than pi over 2, between pi over 2 and pi, or between 90 and 180 degrees. So as an example here, maybe I have a force that looks like this and a displacement that looks like that. Well, in that case, this bit of the force would be F perpendicular, and that bit of the force would be F parallel. So we would be, the parallel part would be pointing against the displacement, which would mean that you're slowing down, which is indeed what we see here. So this is our interpretation for the sign of work. If it's positive, the object is speeding up. If it's negative, the object is slowing down. All right. Now, what if the force isn't a constant? Well, then what you're going to have to do for the case of forces that are varying is we go ahead and make a graph. And we remember that officially, so as long as our motion is in one dimension, we remember we could write the work as the integral of the force dx from x initial to x final. So what this would, we can say, okay, if it isn't in one dimension, we can make it in one dimension. We can still make it work by just saying, well, since all that's happening is this is changing, we only care about the bit that's changing speed, we can write that as the integral of f parallel dx from x initial to x final. All right, so then what you can do is you can make a plot of f parallel against position, and then just whatever it looks like, say it's that, and we want to know the work done over the whole bit, you would find all these areas, the total area under the curve, like so. This would be a positive area under the curve. That would be a negative area under the curve. Positive, negative, like that. You add all that up, and the total work done will be the area under the curve from the beginning to the end of the motion. Now, in this treatment, anything I give you, anything that I would be looking at here would be nice, polite combinations of straight lines such that you can break things up into squares, triangles, trapezoids, stuff like that. I won't be expecting you to be able to take an integral just yet. All right, so let's go ahead and do one example to show at least where the utility of this may be coming. In this example here, it won't be any faster than when we did it before. But hopefully you'll at least see that with some as we develop some additional machinery, namely potential energy, things will get that this will actually become super useful. All right, so let's revisit our friend the Atwood's machine. In fact, we're going to do the exact same example we did when we were doing dynamics earlier. Where we will have a massless pulley attached to the ceiling. And of course, these are ideal physics strings. So the tension is going to be the same throughout. And we'll go ahead and say that mass 1 here is 0.1 kilograms. And mass 2 here is 0.2 kilograms. And now what we're going to do is say, let's go ahead and let these fall for 1 meter. So that one will go down 1 meter. That one will go up 1 meter. At the end of the motion, what we'd like to know is how fast are our masses going. So we know from our common sense, this one's going to go up, that one's going to go down. And notice here I asked how fast, not what the velocity was. To get the velocity now, we're going to have to use our common sense and know that this one's going up, that one's going down. That's something that we call exploiting a constraint. We will see more of that as we go along developing energy, but I just wanted to point that out here kind of as a bit of foreshadowing. So as before, let's start by doing this the unclever way, and then we'll go ahead and be maybe a little more clever with it. So first, let's go ahead and identify 2 free bodies, M1, M2, like that. So this one again will have our purple system. We'll have 2 forces that we need to worry about, so we're just going to go straight to the free body diagrams here. We will have the force of gravity on object 1 pointing down, and we know we'll have a bigger force due to tension pointing up. For the pink system, M2, will be the same deal. We'll have a force due to tension pointing up, and we will have FG2 pointing down, like so. Now, if we remember, this is a pair of forces that act as if they are a third law pair. So I'll put slashes through each of these to let myself know that they are equal in magnitude, if not oppositely directed. And now what we can do is we can find the work done on the whole thing. Since the pulley is massless, we don't care about it. Later, when it's massive, we'll have to do some stuff with torques, but for now, the massless pulley, we don't care about it. So let's just start finding the work done on each of these things. So the net work being done on object number 1 is going to be the work done by gravity. Well, let's take a look at this. The displacement, oops, here is up. So this will be equal to the tension dotted with the displacement plus FG1 dotted with the displacement. Let's call this delta R1 just to be careful. All right, now this is going to be, since they're parallel, this is T delta R. And I'm going to call it delta R now because the magnitude of this displacement will be the same as this one going ahead, looking ahead to it, times the cosine of the angle between them. Well, T and delta R are both pointing straight up, so the angle between these two is 0. So the cosine of 0 is 1, plus FG1, so force of gravity, this will be M1G. Then this will be times delta R, and then this will be times, pardon me while I, oops, move things a bit here. Crap. Try that again. There. This will be times the cosine of the angle between them. Well, this is straight up, that's straight down. That is an angle of 180 degrees. Cosine, that's -1. So we get that the work done is T times delta R minus M1G delta R. Okay, so that's the total work being done on the first object, but we've got another object. The work done on the second object will be the tension dotted with delta R2 plus the force of gravity dotted with delta R2. So here the displacement, my delta R2, is pointing down, and again I'll drop the 2 subscript as soon as we take the dot product because it's the same distance as delta R1 here. This is going to be T times delta R times the cosine of 180 degrees because T is pointing up, delta R is pointing down, plus the force of gravity, not FG1, sorry, FG2. The force of gravity on object 2 will be M2G, and then times delta R times the cosine of the angle between them, but now they're both pointing down, so the angle between them is 0. So cosine of 0 is 1, cosine of 180 is -1, and you get that the work done on mass 2 is equal to T delta R minus M2G delta R. All right, so then let's just go ahead and say the system, if we make our, since we're looking at both masses moving at once, what we can do is just say that whole thing is the system. So then the work done, the net work done on it will be equal to the work done on object 1, F net 1, plus the work done on object 2, F net 2. So this will be T delta R minus M1G delta R. Whoops, my bad, I got the signs messed up here. Cosine of 180 is -1, cosine of 0 is +1. My apologies there. Minus T delta R plus M2G delta R. All right. So the beauty of this is that the work done by the tension cancels. And so we can write this as M2 minus M1G delta R, like so. All right. Now let's go think about the kinetic energy of our system. Kinetic energy of our total system is going to be the equal to the kinetic energy of object 1 plus the kinetic energy of object 2. Well, initially, the kinetic energy of object 1 was 0 because it wasn't moving. So this is 1/2 mv initial squared, but initially it wasn't moving. And by the same token, this is also true for K2 initial. It was also 0. All right. And at any time, the kinetic energy will be 1/2 m1 v squared plus 1/2 m2 v squared. And I can write these as v's because they're the same. From the constraint we had before, whatever speed the one is going down, that's what the other one is going up because the string can't stretch. All right, so the kinetic energy of the system will be 1/2 m1 plus m2 v squared, like that. So we can write that the final kinetic energy of our system is 1/2 m1 plus m2 v final squared. And similarly, we can write that the initial was just plain 0 because neither object was moving. So this means that the change in the kinetic energy of our system is also, so this will be K system final minus K system initial. Since K system initial is 0, this is still going to be 1/2 m1 plus m2 v final squared. Okay. So now by the work energy theorem, we can say that the net work done is equal to the change in the kinetic energy of the system. So this will be m2 minus m1 g delta r equals 1/2 m1 plus m2 v final squared. All right, so then v final squared equals 2 m2 minus m1 g delta r over m2 plus m1. And we can take the square root of both sides while we are at it to get our final speed of both objects at once. So this will be 2 times 0.2 kilograms minus 0.1 kilograms times 9.8 newtons per kilogram times 1 meter. And that'll be over 0.2 kilograms plus 0.1 kilograms, like so. And that gives you a final speed of 2.56 meters per second. Well, that was no easier than when we did this example before. However, let's go back. We could have been more clever about this. We could have chosen, even more clever, we could have chosen instead of to make the system the whole shooting match. Like that. Try that again. The whole shooting match. Like so. Then we would have never had to worry about the work done by tension. We could have just immediately wrote that the net work was the minus mg delta r here and here to get this. And that would have saved us a lot of grief. And again, it would have been because we would have been able to make the tensions internal to the system. So that's hopefully given a bit of a preview of coming attractions to where this is heading. But for now, it's not the and yes, I'm sweeping under the rug what's happening with the support here. But it's at least giving us a hint that with a little more work, a little more effort on our part, we'll be able to turn this into something that's easier to do than dynamics. Right now, it's no easier, no harder, but hang with it for another couple of videos and we will get this to a point where we will be able to do problems like this, like a hot chainsaw through butter. So with that, we'll catch you in the next video.